Last time we calculated the partition function and free energy for a one-dimensional Ising ferromagnet and by transfer matrix method. And at the end of the lecture last time, we derived this free energy density, which is a constant minus J and minus kBt times log of this complicated function of this dimensionless field H and dimensionless coupling K, right? So in terms of this log coach H plus square root of sinh square H plus e to the minus 4K. So then we mentioned that at any finite temperature, T positive, this log function is always analytic because the stuff inside the square root is always positive for any positive temperature and field. As a result, the free energy density is always an analytic function of H and K. And from what we know earlier, that if the free energy density is the analytic function of the tuning parameter, temperature or coupling constant, then there is no phase transition. Indeed, we got this result previously by some simple argument, but here we explicitly calculated the free energy density and show that this indeed analytic function of H and K at any given finite temperature and field. So then, but what is the situation where we really have the phase transition? The phase transition occurs only if this lambda 1, the largest eigenvalue, is non-analytic function of both H and K, or this stuff inside the square root vanishes, which means that we have a double degenerate eigenvalues. Lambda 1 is the same as lambda 2. So in such a case, we can have a phase transition, but these two conditions are not satisfied at any given finite temperature and field. So then, before we come to the zero temperature limit, so let's just introduce the theorem called Perron's theorem, which is some kind of mathematical theorem related to the statement over there. So this theorem says for a n by n finite size matrix A with all positive matrix elements in Ij, the eigenvalue of the largest one has the following properties. Number one, it is real and positive. And number two, it is non-degenerate. And number three, it is analytic function of Aij. So we don't provide the proof of this theorem, just take advantage of that theorem and apply to this one-dimensional Ising model. By a transfer matrix, we can show that this results based on this one-dimensional Ising model satisfy this Perron's theorem, which means that lambda 1 is non-zero, of course, and lambda 1 is not the same as lambda 2, of course, and lambda 1 is analytic, which already shown over here. As a result, there's no phase transition based on this Perron's theorem for the one-dimensional Ising model. As a result, the only chance to have a phase transition is when we go to the zero temperature limit where K goes to infinity. Okay, so we analyze this lambda 1, the larger eigenvalue, again, in the limit of the temperature goes to 0. So remember this lambda 1 has this value written here in terms of the Cauchy and sinh function, but we could do Taylor expansion in the limit of K goes to infinity. Because remember, there's a e to the minus 4K over here. So when K goes to infinity, this value is really tiny, negligible. Okay, but we could nevertheless Taylor expand this leading contribution when K goes to infinity for lambda 1. So then this square root of the sinh square now becomes very important function called absolute value of sinh, because the square root of the x squared is actually given by the absolute value of x. Okay, so that will save our argument because now lambda 1 becomes non-analytic right at this transition. So we could simply just forget about this or throw away this e to the minus 4K, which is negligible. But then the eigenvalue actually show a cusp right at h goes to 0 limit. So then we have this two different behaviors of this free energy, or this lambda 1, depending on whether this field h is positive or negative. So this you could really show that when h is positive, you get this result, but when h is negative, you have different results. Because the absolute value of the sinh function is actually minus sinh for h is negative, but this is plus sinh for h is positive. So then when you add these two terms together, or 4 terms together, you get coach h plus absolute value of a sinh h, which is e to the absolute value of the h. So you could easily see that, when h is positive, these 2 terms canceled, right? But when h is negative, these 2 terms are canceled. But then when h is negative, this e to the minus h is actually e to the absolute value of h. And there's a factor of 2 here, cancel this 1/2, so you get this e to the absolute value of h. Okay, so then what is lambda 1? So lambda 1 is really simple, e to the k plus absolute value of h. So what is the free energy then? The free energy becomes minus m kBt times k plus absolute value of h. Of course, there will be higher order terms, all of t squared, if you Taylor expand this negligible quantity e to the minus 4k when temperature approaches 0. Of course, we don't consider this small value here as a higher order term, so we only keep up to the leading order in temperature expansion. So let's take a short break. When we come back, we will analyze the analytic structure of this free energy in this 0 temperature limit, or a k goes to infinity limit. So let's finish this calculation of the one-dimensional Ising model in the 0 temperature limit. So remember, the free energy in the leading 0 temperature limit ordered, we have this minus n times kBt times this k, capital K plus this absolute value of this little h. And at exactly 0 temperature limit, the free energy in terms of the bare coupling constant J and also the magnetic field, capital H, has the following simple relation, which is minus n times capital J plus the absolute value H, because remember, this capital K is defined as J divided by kBt. And this little h is defined as this capital H, which is the magnetic field, divided by kBt. So then you could cancel this temperature outside the bracket by the temperature denominator in this capital K and little h. So you get the very simple form of free energy exactly at 0 temperature. So now let's look at how this phase transition occurs. So you could see very clearly that you have this cusp type of behavior of a free energy as a function of a magnetic field because of the absolute value here. So if you come from this positive h, you take the derivative of free energies back to the h. From the positive side, you get plus 1. From the negative side, you get minus 1. So this is precisely what we have been talking about, the cusp features of the free energy density as a function of the external field. All right? So at any finite given size and finite temperature and finite as a function of field, this free energy is actually a smooth analytic function of h, as indicated in this yellow curve here. But in the thermodynamic limit and 0 temperature limit, this free energy density is actually showing a cusp right at the 0 field. So when you take the slope of this free energy density from the positive side of 0 field limit, you get plus 1 and minus 1 for on the negative side. And that is precisely what we discussed earlier, that for the one-dimensional Ising model, 0 temperature limit, we have a phase transition between this plus 1 magnetization and minus 1 magnetization, and transition occurs exactly at 0 field. Okay, so let's solve this problem analytically and precisely. Okay, but at any given finite temperature, there's no chance that we have a phase transition for the reason that we just discussed. But at 0 temperature, we do have a chance, and that occurs right here in the 0 field limit. So now let's look at the thermodynamics at the transition when this field goes to 0 limit. So when this external field vanishes, this lambda 1, the larger eigenvalue, has this form, e to the k times 1 plus e to the minus k, which is 2 times coach k. Remember, this k is defined as j divided by kBt when t is almost 0, so k goes to infinity. And this partition function in the thermodynamic limit can be expressed in terms of the simple 2 times coach k to the power of n when n goes to infinity. Of course, depending on this bounding condition, we may have some other minor term which goes away in the thermodynamic limits, as we discussed earlier. So then we could evaluate the bulk free energy density, which is the free energy divided by this number of spins, which is minus J when t equals 0, limit, and minus kBt times log 2 when t goes to infinity. By the way, so this lambda 1 holds for any temperature, but is evaluated exactly at the 0 field. So we have two limiting values for free energy density, depending on whether we're on the low temperature limit or the high temperature limit. Remember, we discussed how phase transition occur in principle. So there are actually two terms that are competing each other at the finite temperature. One is the internal energy, which dominates the low temperature limit. So remember, this free energy is roughly E minus T times S. Remember that. When temperature goes to 0, minus Ts term goes away, and so the leading term should be dominated by this internal energy E. On the other hand, when temperature is much higher in the high temperature limit, it is the entropy which dominates. And in that high temperature limit, you got a minus kBt times log 2, which indicates that this is a free spin. The log 2 is actually the entropy of the free spin, a single free spin, okay, because we have two possible values of the spin. So this is what we expected from the general argument that we discussed earlier. And based on this general form of the free energy density, we could evaluate the internal energy, capital E, at any given temperature, right? So this capital E is actually minus partial log Z partial beta, where beta is 1 over kBt. That follows standard statistical mechanics textbook, and you plug in this partition function, which is this value here, back to this derivative, and you could get this internal energy as a function of beta j in the form of a hyperbolic tangent of beta j times minus j times capital N. And the specific heat is the first thermodynamic quantity that we look at, which is defined as the partial temperature derivative of this internal energy E. So simply just plug in this hyperbolic tangent function into that temperature derivative, and you get this result, which is a slightly complicated function of j over kBt in terms of the hyperbolic second square function of j over kBt divided by t squared times some prefactor. So then we could plot this specific heat as a function of temperature, and this is a typical specific heat behavior as a function of temperature, and there's a peak right at J is about value of kBt, which we call this Schottky anomaly, and this turned out to be a typical behavior of some quantum impurity problem. Okay, so that's the first thermodynamics. So the formal definition of a magnetization is given by this partial free energy derivatives back to the field and divided by this total number of spins. And you plug in this free energy of a one-dimensional Ising model, and you will get this form that we just wrote before, where this omega squared is defined as e to the minus 4k, which is a relative probability between a fully polarized Ising ground state to the situation where we have a single spin flip. So then we could simply just take the derivative of this free energy with respect to the little field, and we get what change of variable from this capital H, which is the magnetic field, to the dimensionless field, little h, which is partial h, this log function, coach h plus square root of sinh square h plus omega square. And when you evaluate this, you find this is the result after taking the derivative. So you could make a plot of this magnetization as a function of the normalized or dimensionless field, and the y-axis is the magnetization, the x-axis is the dimensionless field, and so you immediately get this kind of smooth crossover at any given finite temperature, and there's a saturation values. So when k is some finite value of order 1, and you get the smooth crossover of a magnetization as a function of the dimensionless field. However, in the other limit, when k goes to infinity, you got a yellow curve. When k goes to infinity, meaning when temperature goes to 0, and this magnetization shows a very sharp step function-like behavior right at the transition point where this field vanishes. So you can see very clearly that this omega square is what e to the minus 4k. So when k goes to infinity, this omega vanishes almost exactly. So then this magnetization behaves like what? Sinh of h divided by absolute value of a sinh. This is x divided by absolute value of x, which is a sort of a sine function, so which gives you +1 or -1, depending on whether x is positive or negative. And this is precisely what we see here, right? So the yellow curve is actually not a curve, just a flat function at finite field. But right at zero field limit, it simply just drops from say +1 to -1, and then it goes all the way to -1 when h is negative. So this is what we are talking about, the phase transition. Meaning in the thermodynamic limit, also in the zero temperature limit, the magnetization shows a jump-like behavior or step function-like behavior right at this transition point, a zero field limit, while at any given finite temperature, you can see that there's no jump, no sudden jump. It's a smooth crossover. It's a smooth crossover function of h, where you can see that in the zero field limit, the magnetization actually vanishes. So right here, the red curve tells you that magnetization goes 0 in the zero field limit, meaning you don't have a spontaneous magnetization even in the zero field limit. However, in the zero temperature limit, you do have a sudden jump between the +1 and -1 magnetization, which means that the spins are either fully polarized, pointing up or pointing down in the zero temperature limit, depending on whether this field is positive or negative. And therefore, this actually agrees, perfectly should agree with our earlier calculation over there, that the magnetization shows a jump between +1 and -1 in the zero temperature limit. But here in the finite temperature limit, we also get the general behavior of the magnetization, the function of field at any given temperature, and we see that at any finite temperature, the magnetization is a smooth crossover function of h, where you don't have any magnetization in the zero field limit, but this jump-like behavior occurs only in the zero temperature limit. Okay, so that actually concludes what we can do and about the phase transition of the one-dimensional Ising model. And next, we will calculate the third thermodynamic quantity, namely the isothermal magnetic susceptibility, which is the derivative of the magnetization with respect to the field. And we see what happens in the low temperature limit and also the high temperature limit. So now let's finish the final thermodynamic quantity, namely the isothermal magnetic susceptibility, which is given by the derivatives of magnetization with respect to the field at a constant temperature. And we can just plug in this magnetization that we obtained earlier, which is kind of a crossover function as function of the field. And in the zero field limit, the hyperbolic sign of x is actually approximately x. So the magnetization is approximately given by, to the leading order, h divided by omega, where this omega is e to the minus 2k. Okay, so you plug in and you simply just change the variables to the initial or bare coupling of the field, capital H divided by kBt here, and you take the derivative of the magnetization with respect to the field, and you get this behavior, right? So in the numerator, this is e to the 2j divided by kBt. In the denominator, you get a kBt. So there are two limiting behaviors of this isothermal magnetic susceptibility. One is the high temperature limit. In high temperature limit, this exponential function is simply just say a constant e to the 0, because temperature appears in the denominator in the exponent when t goes to infinity. So this is say 1 over infinity, which is 0 in the exponential exponent, and therefore it is given by 1. divided by kBt, which is nothing but the Curie law for a paramagnet. Remember, in your statistical mechanics or solid state physics, you learn that when the itinerant electron spins in the metal in the high temperature limits, they are free to actually fluctuate, in response to the thermal fluctuations. And if you calculate the response of this magnetization back to the field in that high temperature regime of the metals, you see this is the Curie law, 1 over kBt behavior of the susceptibility, and that is typical susceptibility of ordinary metal in the high temperature regime, which we call this the Curie metal or Curie law behavior. However, in this case, the interesting properties appears when temperature goes to 0. When we approach 0 temperature limits, this 1 over kBt becomes almost divergent. You get e to the 2j divided by kBt divided by kBt. But remember, this exponent is almost divergent. So you get exponentially exploding function when temperature decreases to 0 and the magnetic susceptibility increases rapidly exponentially. Okay? And on top of that, you get 1 over t divergence when t goes to 0 as well. So you get a double singular behaviors as indicated here, that the susceptibility rapidly increases with decreasing temperature and with the speed of this fast, which is e to the 2j divided by kBt divided by t, which is the characteristic behavior of an Ising ferromagnet. Namely, the isothermal susceptibility measures the response of the magnetization to a small field. In the 0 temperature limit, this response is actually huge, which means that in response to this little field in the 0 temperature limit, the magnetization actually change a lot. So namely, you could see that no matter what kind of spin flip state that you are, but in the 0 temperature limits, just a little bit of field applied to your disordered spin flip state, all the spins are going to flip back to the fully polarized phase. So the magnetization change is actually huge in the 0 temperature limit, also in the 0 field limit. However, remember that the magnetization is a function of the fields, and we have this step function like, and this is a smooth crossover, remember that. But exactly at 0 field, you get a jump of a magnetization between plus and minus 1, which means that by taking the derivative of the magnetizations back to this field, you may get a plus infinity or minus infinity. Okay? But if you are slightly away from this 0 field limit, then you can see that in the 0 temperature limit, or k goes to infinity limit, this magnetization is actually flat with respect to this h. Okay? So, which means that the isothermal susceptibility in a slightly, say, positive field regime, this is 0, because if you take the slope or derivative of the magnetization with respect to the field, where this function is actually flat, you get 0 slope, right? And likewise, isothermal susceptibility in the negative side also vanishes. So this tells us that if you are in either side of the phase transition, namely all the spins are pointing up on the positive side or all the spins are pointing down on the negative side, if you are either side of this transition, then you don't have a response to the magnetization with respect to the field because the spins are fully polarized already. So the response is 0. So when the spins are fully polarized, no matter how hard you try to actually flip the spin, if the field is actually finite, not infinity, then all the spins are still locked into this fully polarized configuration, either pointing up or pointing down. So you don't have any response to the small field if you are in either side of the transition at 0 temperature. But then this is not inconsistent with this divergence of the magnetic susceptibility, because in this case you are not exactly 0 temperature limit but approaching to 0 temperature, so that the spins can actually fluctuate from side to side, but right in this 0 temperature limit approaching, the spins kind of get frozen. But before it gets frozen, they tend to point to this all spin up configuration or all spin down configuration, and therefore the response is actually huge, because before they get frozen like this, so they need to get back to their position that they are supposed to be. And therefore, if you sum of all this response, this little response, all the spins, you get a divergent behavior. But once you are in either side of the transition, then all the spins are frozen. They cannot get flipped anymore. And therefore, if you measure this magnetic susceptibility on either side of the transition, you get no response. Therefore, be careful when you are in either side of transition. The magnetic susceptibility should actually drop to 0. Okay, so that is the side remark. So now we understand almost all the thermodynamics of this one-dimensional Ising model at finite field and finite temperature analytically. So now we move on to calculate another very important function called spatial correlations, which measured how closely related are two spatially separate spins along the chain. So suppose this is the Ising chain, and we try to measure the correlations or calculate the overlap of this two spin product Si.Sj average. Okay, so when all the spins are ordered in this ferromagnetic state, all the spins, even if they are very far away from each other, they should have the same overlap, which is simply just +1. Okay, so we will calculate this, but we should formally define this correlation function, which is called Gij. It is defined as the two-spin correlation function Si.Sj average subtracted by the product of each individual expected value of Si average and Sj average. Okay, so we know that for the Ising model in one dimension and any given finite temperature, there's no phase transition and there's no magnetization. So if you evaluate this single spin for all the sites, or every given site, this quantity, this should be 0. In other words, there's no ordered or no spin moment along the chain at any given finite temperature for the one-dimensional Ising model. As a result, in our case, we could simply just forget about the second term. But in general, this is the official formal definition of this Green's function or the correlation function of our two spins. But in this particular case, the second term doesn't contribute. And we call this Gij the two-point correlation function, because it involves the spins on the two spatial points I and j, where I and j could be the nearest neighbor size, could be second neighbor, or could be any arbitrary distance between the two. And you could understand this kind of Gij as the fluctuations of the spins on side I and j, because you could show that the Gij function is actually related to this type of standard deviation thing, which is the product of the two fluctuations. One is the spin moment on side I, another is spin moment on side j, and the first bracket is actually measuring these fluctuations of the spin on side I. And the second measures the fluctuations of the spins, because this refers to the so-called standard deviation. So if this Si describes some distributions of the spin or a function, and Si average is actually the average value of that function, and so this function, Si subtracted from this Si average, tells you the fluctuations called delta Si, which is the fluctuations of Si with respect to the average value. Okay, if you make a plot of this delta Si or Si versus I, and you may have the average value of this Si, which is indicated by this constant line, but there are some fluctuations, up and downs, indicated by these orange curves. So if you subtract this orange from this flat horizontal line, you get these fluctuations of the function Si relative to the average value of the Si. Okay, So in other words, this Gij measures the product of the fluctuations of the spins on side I multiplied by the fluctuations of the spin on side j. And this is also related to the called the Pij function, which is the probability of that delta Si Sj. And we call this delta Si and delta Sj. This is going to be the Pij. So let's just derive the relation between this delta Si Sj or the Pij and the Gij. So you could very clearly see that this is 1/2 of 1 plus Si Sj, which is 1/2 plus 1/2 of Gij plus Si Sj. Okay, so you could check our textbook for the details, but you could easily understand that Gij is closely related to this Pij. So they differ by just this product of this average of Si and average of Sj. So this delta Si Sj is measuring the probability of the spins, in this case, on side I and j that have the same value. In other words, it measures the overlap of this spins on side I and side j, and then we will formally calculate this Gij based on this partition function, because we know that we calculated this partition function already, and then by taking the ensemble average of this Si dot Sj, we could take advantage of the partition function that we already evaluated. And in the simple one-dimensional Ising model in the finite temperature, we simply can ignore the second term, and we could calculate analytically this ensemble average of Si dot Sj. Okay, so let's take a short break. When we come back, we will continue evaluating the Gij. So let me continue. Just a moment ago, we defined this Gij, which is a spatial correlation between the two Ising spins along the chain on side I and side j. But it is related to this another probability function Pij, which you define the average value of the delta Si Sj. But I have a correction to make. It is given by the probability of the two spins having the same value. The probability of the two spins Si and Sj having the same value. Okay, so it is not exactly the same as overlap between these two fluctuations of spins that I defined earlier. So let me just clarify this difference. This Pij function is defined as average value of the delta Si Sj, and this is given by 1/2 of 1 plus Si Sj and everything ensemble averaged. So it can take just two values, right? In the simple case of the Ising spins, because Si could point to the same direction as Sj. In that case, Si and Sj are both +1 and therefore, or -1, and 1 plus 1 divided by 2 is actually 1. So this measures 100% of agreement between the spins at side I and side j if they have the same value. And if they have the opposite value, meaning one is up, another is down, then this is 1 minus 1, which is 0, divided by 1/2 is also, by 2 is actually 0. So this Pij takes 0 if these two spins are pointing to the opposite direction. So it simply just measures how different or how closely related the two spins are on the Ising chain. So then we could simply just rewrite this probability Pij function in terms of the Gij. Remember, the Gij is standard deviations of a product of two spins, right? Okay, and taking this ensemble average. But this Pij is related to the Gij by constant 1/2, and also product of these two spin average term, Si average times Sa average, But in the one-dimensional Ising case, at finite temperature, and both SI average and SJ average are 0, so you simply get 1/2 plus 1/2 GIJ. So the PIJ, measuring the probability of the SI and SJ having the same value, it is closely related to this GIJ. In this Ising model of finite temperature, both SI and SJ average vanish, and as a result, this delta SI/SJ is simply just what? 1/2 of ensemble average of the product of the SI and SJ. But it is not exactly the same as the product of the standard deviation that I just mentioned, right? So they differ by some kind of constant shift and so on. So now let's go back to GIJ, which measure how these two spin variables on different sides are related to each other. Okay, so go to correlation function. And remember, this is ensemble average of these two spin multiplied together. So this is proportional to this, or exactly this, in the Ising model of finite temperature. And so, but what is the ensemble average of SI dot SJ? Well, you could go back to this definition of this thermal average function. And in that definition, you have to calculate the partition function first, and then the numerator is the Boltzmann weight times this SI dot SJ, and the denominator is the partition function itself. So this is just by standard STEMAC definition of any ensemble average of any statistical mechanics observables. But what we have, this numerator, is nothing but Boltzmann weight times SI dot SJ. But what is the Boltzmann weight? But this is nothing but the Hamiltonian of the e to the minus beta h. Remember that in the Ising Hamiltonian, you simply just plug in this Hamiltonian of the Ising ferromagnet, and you get this expansion here. And you sum over all spin configurations on all the sides from S1 to Sn. To simplify this calculation, let's just look at this nearest neighbor correlation. So Gi I plus 1 is the nearest neighbor correlation function, which measures or keep track of these two spins on neighboring sides, how related they are, and what is the overlap between these two spin variables on the neighboring sides. You take ensemble average of the SI dot the SI plus 1 and plug in this definition over there, and you get this result. Okay, so this is nothing but you take the derivative of the stuff and respect to the Ki. So if you take the differentiation of all this yellow bracket respect to the Ki, you get what? Si dot Si plus 1, because that is precisely this term that we have here. Once you take the derivative of this, the Boltzmann weight with respect to this K, the coupling constant K, because in the general term, e to the Ki Si plus 1, if you take the differentiation of this term with respect to Ki, you get exactly what? Si dot Si plus 1. So that's the smart move, because now you don't need to really worry about this complicated sum, because this is nothing but taking the differentiation of the partition function with respect to coupling constant Ki. And we know what this partition function is from the previous calculation, because this is given by the 2 to the power of n times the product of the coach Ki. And you simply just plug in this result from our previous calculation, and you take the functional derivative of this partition function with respect to the coupling constant Ki, you get hyperbolic tangent of Ki. And we know that for the nearest neighbor Ising model, we consider all the coupling constant equal, namely all this couplings between the neighboring spin, nearest neighbor spins, is considered homogeneous, and also this kind of J and J and J and J. So by taking all this coupling constant equal and isotropic, you get hyperbolic tangent of K as a Gi plus 1. And this is a really simple function which we already obtained earlier, the hyperbolic tangent function. So you plug this hyperbolic tangent function as a function of K, and you get this orange curve here. So there are two limiting cases. When t goes 0, remember k is just J divided by kBT. So when temperature goes 0, k goes to infinity. When k goes to infinity, this hyperbolic tangent saturates at this value 1, which is exactly what we show over there, that at 0 temperature limit, when this Si shows the same value as Sj, and you get probability Pij to be 1, which is exactly what this Gii plus 1 is telling us, that two spins on neighboring sides, the 0 temperature limit of a one-dimensional Ising chain are having the same value. So this correlation is actually perfect. So this tells us that this correlation is perfect. Meaning, suppose I know the spin variables on side I, which points to the up spin configuration, and nearest neighbor side also is a spin up state. So let me just plot here. So this is spin up state, and so is the spin on this I plus 1 side. Okay, so you could just use the same argument to argue that the left side, the nearest neighbor side on the left side of the side I, is also a spin up state, and so on and so forth. And then all the spins along the chains are all spin up state. On the other hand, in this high temperature limit, when k goes 0, we know that the domain walls are created, all the spins ordered are destroyed, and you can see very clearly that this correlation function vanishes, which means that there's no correlation at all, no correlation at all. The spin orientation on side I has nothing to do with the spin orientation on the nearest neighbor side. So the spins on the nearest neighbor sides are totally uncorrelated. So they have no relations at all. So that's indicates here that the correlation function vanishes, meaning there's no probability of finding the spin on side I and nearest neighbor side I plus 1 having the same value. The probability of finding the same value of these two spins is actually 0. So meaning the spins are totally disoriented. Finally, just use another method to derive the same relation. So remember the internal energy that we just calculated by evaluating the sum average of the Hamiltonian, and which is minus J sum over I Si plus 1. Remember that. So this is minus mj hyperbolic tangent beta j. So now we could argue that since the system is actually translationally invariant, that this kind of nearest neighbor pairs, when you take the ensemble average, is actually identical if you simply just shift this I by I plus 1 or I minus 1, or by any arbitrary integer multiple of lattice constant. So which means that the spin-spin correlation between I and I plus 1 is the same as the correlation between I plus 1 and I plus 2, and so on and so forth. So because there's no difference between all this nearest neighbor spin correlation functions. And therefore, you effectively just add all this n copies of this nearest neighbor spin-spin correlation. So this is minus n times j times just a single spin-spin correlation on neighboring sides. No matter which side you choose, it is the same. And this is given by what? Minus n j hyperbolic tangent beta j. So you can compare these two equations, you get precisely the same conclusion, that correlation function between the two nearest neighbor Ising spins, I and I plus 1 sides, is actually hyperbolic tangent beta j, or hyperbolic tangent k. So I guess time is up for the day, and let me summarize. So we finished all this thermodynamic properties of the Ising model in one dimension, and we rigorously proved that there's no phase transition at finite temperature, but there is a phase transition, 0 temperature and the 0 field limit. And we calculated that limit and all the thermodynamics in that limit, and we also calculated the correlation functions of the nearest neighbor pairs of the Ising spins, and we concluded that the correlation between the nearest neighbor spins of the Ising model in one dimension follows hyperbolic tangent function. So in the zero temperature limit, you get perfect correlation, but in the high temperature limit, you get no correlation. But in somewhere in between zero and high temperature limit, you get a crossover from 0 to 1 in this hyperbolic tangent form. Okay, so let's stop for today, and we shall continue next time when we calculate further the spatial correlation of Ising spins. We generalize this calculation to second neighbor correlation function, or third neighbor, or arbitrary distance between these two spins on side I and side J of an Ising spin chain. Okay, so I'll see you next time.